Good morning to all. We have gathered here for the second memorial lecture in homage to Professor M.C. Valsakumar. The family, colleagues, friends, and students of Professor Valsakumar have gathered here. There are some new students and teachers also who may not be familiar with the person and his work. So let me briefly introduce Professor Valsakumar and his legacy. Professor Valsakumar was born at the village Pinarai in Kannur district in Kerala, in northern Kerala. He was an alumnus of Government Brennan College, Thalassery, and later at Physics Department of Calicut University. And soon after his MSc in 1975, he joined the prestigious Bar Training School of DAE, Government of India. Now, since then, after his training, after completing his training, he worked at IGCAR Kalpakkam for a long span till he superannuated as outstanding scientist and head of materials physics division in 2012. Apart from his regular work and projects at IGCAR, Professor Valsakumar did some extremely good quality research, and he has published around 160 research articles in reputed international journals, including many in Physical Review Letters, Physical Review B, etc. And his research interests span from quantum field theory to computational material science. He had also worked with the great Indian physicist, Professor E.C.G. Sudarshan, while the latter had been at IMSC Chennai. Many scientists and various university students completed their PhD under his guidance. He was also an expert in high-performance computing, and he was instrumental in developing dedicated computational facilities at IGCAR. Soon after he retired from IGCAR, he was invited as a distinguished professor at HCU, Hyderabad Central University. He was there for 2 years. And in June 2015, he accepted the invitation to be a faculty of IIT Palakkad, where he served until March 2018. Professor Valsakumar was an inspiring teacher with a deep understanding of different branches of physics and mathematics. He was adored by his students, who fondly called him Valsa. He was an honorary member of Academy of Physics Teachers, Kerala, and his demise is a great loss to the physics community. He passed away, Professor Valsakumar passed away on 1st January 2019. And in Academy of Physics Teachers Kerala, we decided to conduct annual memorial lectures in homage to Professor Valsakumar. And the first annual memorial lecture was conducted last year in October 2019 by Professor Ananda Krishna from IAC Bangalore. Today is we are conducting the second memorial lecture. Our resource person today is Dr. Debendranath Sahoo. He was a former colleague, a senior colleague of Valsasar at IGCAR Kalpakkam. And today he will be presenting the lecture, Heisenberg's Invention of Quantum Mechanics. He will be talking to us on matrix mechanics, the invention of matrix mechanics by Heisenberg. On behalf of all of us gathered here, on behalf of the organizing APT, Academy of Physics Teachers Kerala, I welcome Dr. Debendranath Sahoo to this program. Valsasar's family is here. I welcome his wife, Srimati Leela Valsakumar, and his daughter, Srimati Veena Valsakumar, to this program. And as I mentioned, many of the former colleagues of Valsasar are here. Only a few names I mentioned: Professor K.P.N. Murthy, Dr. S.V.M. Satyanarayana, Dr. Krishna Kumar, and many former colleagues and friends of Valsasar from Bar Training School period, from IGCAR Kalpakkam, from Hyderabad Central University, and from IIT Palakkad. I welcome, on behalf of the organizing committee, I welcome all of you to this program. And his student and colleague, his collaborator, Dr. Ajit from NITK Surathkal is here. I welcome him. All the students of Valsasar who are present online, here. I welcome all of you. And the teachers and students from Kerala and also outside the state, all of you who are present here, I extend a warm welcome on behalf of APT. I extend a warm welcome to all of you here. And welcome to all. And I invite the APT President, Dr. Titus K. Matthew, to preside over the function.
Thank you, Dr. Harikrishnan. Am I audible?
Yes, sir.
Okay, thank you. So, good morning to all. This is a great occasion. So, respected family members of Professor Valsakumar, especially Mrs. Leela Valsakumar, and the family members of Valsakumar sir, his colleagues and friends, members of APT, and my dear friends. So we all are here for the memorial lecture of Professor M.C. Valsakumar. He's a great, as far as I know, he's a great personality in physics who spent a larger amount of his life for physics, both in research and teaching. And regarding APT, we are largely or especially benefited from him due to his great contribution towards our workshop series for the college teachers and students. In that sense, we are deeply indebted to him. So this second memorial lecture is going to be delivered by Professor Debendranath Sahoo, his colleague and a former professor in Sri Sathya Sai Institute of Higher Learning, and we are indebted to him also for kindly agreeing for this lecture in this great moment. So we are all eagerly waiting to hear this lecture in memory of our great teacher, Professor Valsakumar. Before opening the lecture, let me invite Dr. Harikrishnan to introduce the speaker. Hari?
Yes, sir.
Okay, thank you. Over to Hari.
Today's resource person, Dr. Debendranath Sahoo, is currently a visiting faculty at Sri Sathya Sai Institute of Higher Learning, Puttaparthi. Dr. Sahoo had his MSc from Delhi University, and then he did an MA in physics from Columbia University in New York. He did PhD from Yeshiva University, New York, and his PhD guide, one of his PhD guide was H. Pat Peterson, an assistant to Niels Bohr. And he worked with Dr. Raja Ramanna at BARC in Mumbai. From 1974 to 1999, he was scientific officer at IGCAR Kalpakkam. From 1999 to 2005, was also a visiting scientist at Institute of Physics, Bhubaneswar. He retired from IGCAR Kalpakkam in 2005. And after that, he's a visiting faculty at Sathya Sai Institute of Higher Learning, Puttaparthi, and he's continuing his research in physics. He has collaborated with Valsa sir on many theoretical works, and I request Professor Debendranath Sahoo to talk briefly about his association with Valsa sir and also to present his lecture. Thank you. Manoj.
Namaskaram. I thank the organizers of this forum for asking me to give the second Valsakumar Memorial Talk. Shown in this photo is my friend Valsakumar along with Leela Valsakumar, his wife. I convey my respect to Leela, and my blessings to Veena Valsakumar. 3 months before Valsa passed away, I had a chance to have an interaction with Valsakumar. I had sent him an email asking him whether he would like to collaborate with me on a paper I was planning to write, which would have become a review article. I had outlined roughly the idea of the work. Next morning, I received a call from Valsa where he appeared very enthusiastic and gave his answer in the positive. He asked me whether I can generate the first draft of the paper and send it to him, and also for some reading material. However, I took too long to write the review draft of the paper, and it was too late to reach him. I have found Valsa always interested in discussing academic matters. His style of work was very interesting. Whenever I used to ask him to clarify some doubt, he would almost on the spot explain it very clearly. If he doesn't know how to do it immediately, he asks for some time, and maybe next day he comes to me and we discuss about it. But he was very sharp in his analysis. Valsa never discussed any of his personal problems with me. The only time he asked me a favor was when he felt very depressed working in the low temperature laboratory at Kalpakam. He was not happy there. One day, after the office work was over, normally we return by the same bus and get down. At the bus stop, we had a common bus stop to get down. And as we were walking to Valsa's apartment, it was very close to mine, we started talking. I remember this scene vividly. There was a jungle gym right below his second floor apartment. In this gym, I know Veena used to play when he was a child. And in the conversation, Valsa mentioned his unhappiness and how working in the low temperature laboratory he did not like. And he asked me whether it would be possible that he can join the theory section and work on theoretical problems. I obtained the necessary permission from Dr. Venkatraman, who was heading the laboratory, and Valsa formally joined the theory section. The first problem we worked together was gauge theory of defects in solids. And here, Valsa made very rapid analysis and almost finished the problem in a couple of weeks. The first problem we handled on the problem of dislocation in a solid, elastic solid. So it was a proof that if he is interested in a problem, he goes ahead and solves it with a lot of interest, and the solution he gives is completely original. I remember Valsa as a good as a great teacher. I had instituted a summer training in physics program. It was meant for MSc students from colleges who would get stipends from atomic energy and work in Heisenberg in our laboratory for 2 months. Valsa took great interest in conducting that course and taught the students with tremendous zeal and enthusiasm. Couple of those students later on got admission into training school, and they also joined IGCAR formally, and they are still there, I think. I remember one incident which I must narrate. The last day that I left Kalpakam was when I had to go to Kalpakam to collect my retirement benefits. That was in the year 2005. I had shifted to the Institute of Physics in the year 2000, and when I had to come in 2005, after 5 years, for the official closing my chapter at Kalpakam, there was a farewell meeting also for me, arranged by Valsa and my friends. I entered the laboratory, and in a room I saw a very interesting picture. There was a pinboard on which there was a photograph of a chair on which was kept a pair of chappals. The chappals that I had left at Kalpakam in the year 2000, when I formally left for the Institute of Physics at Bhubaneswar. And behind the chair were standing Valsa and some of my friends, about half a dozen of them, of the theory section. And narration and talking about that scene created so much amusement and fun. But later on, that incident touched my heart, and beneath that fun and enjoyment of that incident was lurking Valsa's great respect for me, and I knew he was the mastermind in getting that photo taken. So I have many more things to say about Valsa, and they are still vividly there in my memory. With me are still Valsa's many manuscripts which he had worked, but it never got published. I forgot to mention in his academic contribution, there's so much work he did on the gauge theory of defects. It was shown to Professor E.C.G. Sudarshan, who was the director of Institute of Mathematical Sciences at Chennai. He looked at the work that Valsa had done and gave the opinion that it qualified for 2 PhD theses. And he offered Valsa that he can be a student and he will guide him formally for the PhD degree, and asked him to write it up. But Valsa was never interested in a mere PhD recognition. he was busy doing his research as usual, and that was the hallmark of Valsa, who never cared for outside recognition. He was happy within himself in what he was doing. That was my friend Valsa. I thank you for again for having invited me to have a chance to speak on the occasion of the memorial to commemorate Valsakumar. Thank you.
Thank you, sir. I think now we can go on to the lecture, right?
Yes, now we can. Yes, now we can move on to the lecture, sir.
Yeah.
I will be speaking to you on Heisenberg's invention of quantum mechanics. As you know, quantum mechanics governs our daily life in a very intimate way because all the technologies that we use bank upon the principles of quantum mechanics. But how did quantum mechanics originate and who found it first? Quantum mechanics has developed from Newtonian mechanics. The Newton's equations are replaced by appropriate equations applicable to quantum mechanics by simple reinterpretation of the variables used in Newton's equation, such as x, the position variable, is replaced by the quantum mechanical x. The date of birth of quantum mechanics is 29th July 1925, the date on which Heisenberg's paper with the title Quantum Theoretical Reinterpretation of Kinematic and Mechanical Relations appeared in a German journal, Zeitschrift für Physik. I have given the English translation of that title. This paper is about 12 pages long, and it won Heisenberg a Nobel Prize in the year 1932, when he was only 20 years old. Heisenberg had opportunity to work with Niels Bohr in Copenhagen. And when he was 24,
Manoj, is there an issue?
Yeah, it will be okay soon.
Okay.
interpretation of kinematic and mechanical relations up in a German journal, Zeitschrift für Physik. I have given the English translation of that title. This paper is about 12 pages long, and it won Heisenberg a Nobel Prize in the year 1932, when he was only 20 years old. Heisenberg had opportunity to work with Niels Bohr in Copenhagen. And when he was 24, he developed this new theory of quantum mechanics. About the paper that Heisenberg wrote, this is what Steven Weinberg, a Nobel laureate of 1979, has to say. Although I think I understand quantum mechanics, I have never understood Heisenberg's motivation for the mathematical steps in his paper. Heisenberg's 1925 paper was pure magic. This is a miracle paper. The objective stated by Heisenberg is to establish a basis for theoretical quantum mechanics found exclusively upon observable quantities. The words observable quantities are very important in what I will be speaking. Quantum mechanics comes in two flavors. The wave mechanics of Schrödinger, which is the popular approach, shown in the figure to the left of Heisenberg is Schrödinger. The person with the hat is Heisenberg. Heisenberg's approach was matrix mechanics, which is rather abstract and is never covered in the college syllabus. The purpose of my talk is to impress upon you how Heisenberg invented the non-commutative matrix mechanics. But I will be able to cover only very little of his paper and hope that I will give you the flavor of the importance contribution that Heisenberg has made. Heisenberg made a very risky assumption, but he had very high M. The circular and the elliptic orbits of electron that we are familiar in the Bohr model and the Bohr-Sommerfeld model, they are fictitious. They are simply not there. Only the observables, which are frequencies and the intensities I of omega of the spectral lines measured by experiment, have a place in theory. In this approach, Heisenberg follows Einstein's dictum when he developed a special relativity theory. In relativity theory, in order to synchronize two clocks with relative motion, one has to use the light which has maximum velocity. That is how experimentally one can synchronize two clocks, and that is how Einstein discovered Lorentz transformations. So Heisenberg follows his footsteps. The challenge for Heisenberg was to develop a new theory by upgrading Newtonian mechanics. So the basic features of Newtonian mechanics are to be retained, but the variables are to be suitably reinterpreted. Shown here in this picture is the spectral lines of hydrogen, and what I want to you to notice is that they occur with various intensities. Although the frequencies are somehow explained in the model of Bohr and Sommerfeld, But the intensities of light were not accounted for when Heisenberg was looking into this problem. Also, there was an impetus for Heisenberg coming from the anomalous Zeeman effect, and which, as you know, in Zeeman effect, there's a magnetic field, and the spectral line splits. One line becomes three. But for alkali metals, there are more than three lines. And this was not explained when Heisenberg was working on this problem. Now, Heisenberg looked at a classical picture of how an electron moving in an atom will emit radiation. The motion of atom being periodic, one can model it as a one-dimensional system, and the variable, the position variable x of t can be expanded in a Fourier series with the fundamental frequency omega 1, the overtones omega 2, omega 3, etc. The general frequency is omega tau, which is an integral multiple of omega 1. So tau is an integer. The A's, A1, A2, etc., are the amplitudes. Now, Maxwell equations imply that light is emitted with the same harmonic frequencies, omega tau. The intensity of light, according to the Larmor formula, which is based on Maxwell equations, is given by the square of x double dot, the acceleration of the electron. And using the Fourier expansion, for each Fourier component, the intensity I, which depends on omega tau, is given by the square of the acceleration and the fourth power of the frequency corresponding to that harmonic. So here I have shown the frequency harmonics as tau times omega, and the time average intensity I of omega tau as tau square A tau squared omega to the power 4. This is what the classical theory gives. Quantum theory, the old quantum theory, by old quantum theory I mean the theory that was there during the period 1900 to 1925. And Planck in the year 1900 gave the energy quantum hypothesis that the elementary quantum of energy comes as a constant times the frequency omega, and the constant is now known as the Planck's constant, h bar. Planck gave this hypothesis, which was later verified by photoelectric effect and other experiments. But Planck's idea or purpose was to explain the black body radiation. The spectrum is written by formula, and unless you use the h bar omega as the energy quantum, one cannot explain the full spectrum or the behavior of intensity versus the frequency. Also, there was the model of Sommerfeld and Wilson, who gave a quantization rule in the year 1915. And in that quantization prescription, the classical action J, which is the integral of P over X, it's a cyclic integral, which is integration over one period, is quantized. Also, the J can be expressed as, if you change the variable, replace the momentum by mx dot and dx by x dot times dt, and integral variables are from 0 to capital T, where capital T is the time period of the periodic motion. Then one can express J as 2 times the time period multiplied by the average kinetic energy. And that is equal to n multiplied by h, where n is an integer, taking values 1, 2, 3, etc. These states, this is the concept of stationary state of a periodic system. So the states are now labeled by n. Shown in this picture is the phase space plot of the action that's corresponding to a given energy. Let us say E1, there is an orbit in this phase space. And similarly, for another energy, for each energy, there is an orbit. This is the concept of stationary states, which appear as discrete and preferred states. The stationary states. Bohr gave his model in 1913. It's the electron jump model. That the electron jumps between two stationary states, thereby giving a frequency omega. And notice it has now two indices, n and another n minus tau. That is a level below the state n. So the frequency that is emitted, or the light that comes out of a jumping electron, is a difference of two energies corresponding to the states n and n minus tau, and divided by the Planck constant. So that is an entirely different mechanism. It is not the orbit model, it is not the classical model of accelerating electron, because in stationary states, the electrons preserve their energy state, and there is no emission in a particular stationary state. Only when there is a jump, there is emission of radiation. So I have shown here the classical model. Now notice that the amplitude appearing in the Fourier expansion depend on the quantum number n of the state variable. So the classical picture is a wave with a times the cosine omega t, and with the appropriate index n. So this is the orbit model. But Bohr's quantum jump model is shown in the right, where A is the transition rate from the stationary state n to a state below it in the energy scale, state level by n minus tau. And when there's a change of stationary state, when the electron makes a jump, there is a energy is converted into light, and out comes the frequency, which is now dependent on two indices, n and n minus tau. X now acquires a new status, that is the Fourier series. Now each term in the series is denoted with an index n corresponding to the quantum number. So x, a, and omega, they all depend on the stationary state n. Bohr, this was a very important thing that Bohr enunciated. And this is called the Bohr correspondence rule, that for very large values of n, the light frequency that is emitted is same as the orbital frequency. That is expressed by the equation omega n, comma, n minus tau becomes equal to tau times omega of n. So the two indexed omega is the quantum jump model. The mechanism is quite different from the classical model, which is a harmonic frequency model. So omega in the classical model has only one index, n. Einstein in the year 1916 had derived the Planck formula by considering thermodynamic equilibrium of the black body radiation in a cavity, and he introduced two coefficients, A and B. A is the transition rate from a state M to a state N. It's called the spontaneous emission. And also there are transitions arising from the incident electromagnetic wave. Those are, they work both ways, from the upper level to lower level, as well as from lower level to upper level. These are induced transitions. N, capital N, is the population of the state. So by considering this equality of two rates as the energy balance equation, Einstein explained or derived the black body spectrum of Planck. I will not go into details of the derivation, and I will skip it and come straight to the radiation from atomic transition, which from Maxwell equations, as I said earlier, the power or the intensity is given by square of the acceleration, x double dot. And if you take x as exponential of I omega t and treat x as periodic, then assuming an isotropic radiation, the intensity I of omega is proportional to the power p of omega, and it's given as the fourth power of omega and the square of x. Heisenberg extended this classical formula to quantum mechanics. The x was replaced by x mn, where m and n are the quantum state levels. And similarly, the exponent with the omega has now two indices M and N. And in the formula for power, the omega and x appear with two indices. So it takes over the Maxwell relations of the Larmor formula into his quantum mechanics. And the transition rate from the level M to the level N is now given by the corresponding expression with square of x Mn. Let us not worry about this induced emission relation. I will skip it. The only thing to notice is that this was known to Heisenberg, that the induced emission given by the transition rate B is different from the spontaneous emission. And to explain this is that x becomes equal to its complex conjugate. Only thing you have to interchange the indices M and N. Heisenberg used Bohr correspondence principle as his guide. Bohr's correspondence principle states that classical physics holds for large quantum numbers. For very large M, the transition frequencies omega Mn are harmonics, which are given in the orbit model. Also, the intensities I of omega Mn and the polarizations come out all right if one looks at high quantum numbers. So both the frequencies and the intensities, although they originate from electron jump in his new theory, but for high quantum numbers, they match exactly with classical orbit model expressions. Shown here in this picture is the full hydrogen spectrum. The thing to note is that for low quantum numbers, the states or the energy levels are not equally spaced, whereas for high energy states, the levels are equally spaced. And ultimately, atom gets ionized and you get the continuum. For example, if there is a transition from the state 500 to a state 499, just the level below, and call the frequency as omega 0, then 2 steps below, the transition from 500 to 498 is 2 times omega 0. 3 steps below, it is 3 times omega 0. 4 steps below, it is 4 times omega 0. This shows that the for high quantum numbers, the spacings are equal. However, for low energies, if you take a low quantum number like 5, the transition from 5 to 4, let us call it as the fundamental frequency, omega 0. Then from 5 to 3, it is 3 times omega 0. From 5 to 2, it is 9 times, and from 5 to 1, it is 43 times. So they are very unequal. Now, these lines that are seen for low quantum numbers, their values or their wavelengths were given by a formula which was given by Balmer in 1885. Balmer was a high school mathematics teacher, and he, in his spare time, was working on a formula, a mathematical expression, which will reproduce the observed wavelengths. So it is given by n square divided by n square minus 4, where n takes values 3, 4, 5, and 6, and it reproduced 4 spectral lines, prominent spectral lines. It is called Balmer series. Rydberg later improved this formula in 1908, and the formula had reciprocal of the 2 integers occur there in the formula, and the frequency omega is given as transition from one state to another by appropriate integer values. That reproduced the hydrogen lines more accurately. This was known to Heisenberg. So Heisenberg, the quantum detective, because he has a very challenging problem. The challenge is how to make a theory for low states with smaller n. This is like transforming a donkey into a horse. It's a very tall order. Heisenberg makes a very simple observation, and notice, I remind you again that Heisenberg's aim was not to improve upon the Bohr model or not to explain better the Bohr-Sommerfeld model with his replacement of observable. His aim was to develop a new theory like Newton's equations, which would explain the behavior of all microscopic systems, not just the hydrogen atom. But the clue he gets was by looking at various facts related to the observations done on hydrogen atom alone. So what all I said, the Bohr-Sommerfeld quantization, the Planck hypothesis, and then the Bohr model, the Larmor formula, all those things, and the Einstein's A coefficient, all those things have to be was in Heisenberg's mind, and they were made use of in developing a theory applicable to all quantum systems. But he made a simple observation in the following way. If you take the one-dimensional harmonic oscillator with frequencies omega alpha, which is alpha times omega for a quantum state n, then x, which depends on n and t, can be expressed as a summation over the various terms of the Fourier series. Now, the index goes from minus to plus infinity. Here, hidden in this expression is the fact that Heisenberg is using the complex field as the basis instead of the real field that occurs in the Newtonian mechanics. This is important. Now, since the intensity is related to square of x, so one has to square the sum in the Fourier expansion, and it's a mathematical step that one has to use double summation using two indices, let's say alpha and gamma, and two similar terms, and their product has to be worked out. Combining the frequencies in the exponent, since omega subscript alpha is alpha times omega, and similarly omega gamma is gamma times omega, one sees that the two omegas can be added to give a single omega having a subscript alpha plus gamma. Now, it is natural to make a change of variable and define a new index beta as sum of alpha and gamma. When that is done, one gets again a Fourier series with the amplitude which is occurring inside the square bracket involving the components A beta minus alpha, another component A alpha. But the exponential has a single omega. I restate the classical frequency and the amplitude composition rule here. As I said, the omegas add up, and the Fourier coefficient for x square, that is b beta of n, is expressed in terms of the A's with appropriate indices. The important thing to note here is that two Fourier amplitudes compose again to give another Fourier amplitude. This is mathematically natural, but this is a very, very important observation. And by simply trying to write x square in a Fourier series was a very crucial step. Now, how to compose the Fourier frequencies and amplitudes in quantum mechanics? The amplitudes are now having two indices, and skipping the details of the how the variable A behaves, I will proceed further that if you make these changes of indices n and n minus alpha and omega similarly with two indices, the real part of a typical term, which is given by A times the exponential I omega t, by the corresponding real part of two index objects. So this is the procedure or the prescription of Heisenberg. He has to give the composition rules for the frequencies and the amplitude, which will also generate when you take the square of x also as a Fourier expansion. Here, noting that the frequency, which depends on two indices, is the difference of two energy values. But in orbit model, it is an integer times the fundamental frequency. The classical frequency of a one-dimensional periodic model is given by the classical Hamilton-Jacobi approach, but that is covered in the classical mechanics. You might be familiar with it, but if you do not remember, it does not matter. But note the old quantization scheme was upgraded, or if you make the corresponding change by changing the one index objects to two indices, the simple derivative is replaced by a difference operator. And here, Einstein makes another crucial use of the Ries combination rule, which was found empirically in the year 1908, that the difference of two frequencies corresponding to two quantum states n and n minus beta is also a new frequency given by n minus alpha. In other words, the frequency omega in the jump from n to the level n minus alpha, and subsequently from n minus alpha to a lower level n minus beta, is given by the net jump frequency, which is omega of n, comma, n minus beta. This is consistent with Bohr's model. Now, this is how Heisenberg gives the composition rule for x square, and he simply writes it by making use of the Ries combination principle, because that is the guide to compose the frequencies in the exponents so that they will collapse into a single frequency. Two frequencies have to be added, and it's a two-index frequency. But the Ries combination principle is very useful here, and making use of that, one can generate a Fourier expansion with B as the new Fourier amplitude, depending on n and n minus beta. So there is a change of variable, again, which has been made use of. And one obtains the Heisenberg's frequency composition rule, which, as I have emphasized, is a rewording of Ries combination rule. And the net result of this replacement gives you the fact that, again, the composition of two Fourier amplitudes give you a new Fourier amplitude. So the Fourier series is very important in this derivation. Now, Heisenberg goes one step further. This one is able to do for a single variable x when it is squared. So x squared is x times x. But what happens when you take two different variables, x and y? Suppose a's are the Fourier coefficient of x, b's are the Fourier coefficients of y, c's are the Fourier coefficients of x times y, and all that is done following exactly the steps used in writing x square. But when you interchange x and y, the Fourier amplitudes, let us say, are c dash. Then c and c dash, this is important to notice, that C and C dash with corresponding products occurring in the summation, which involve A and B, because now A's are the Fourier coefficients of X, B's are the Fourier coefficients of Y. And when you look at the expressions for C and C dash, they are different. This is very, very interesting, and Heisenberg was very much, he had to struggle to understand why they are different, because this is the how non-commutativity was discovered. Because if the coefficients are not same, then what happens is when you take the product of X and Y, it will not be equal to the product of Y times X. Using the matrix notation, one can write the amplitudes and the frequencies together. If I redefine Q of alpha and beta, let us say, and one can group it in the form of a matrix in the modern notation. So the quantum mechanical X is a matrix, and matrices do not commute. This is a very trivial fact, but the thing to note is that Heisenberg did not know what a matrix is, and it was not taught in colleges at that time. So it is like Newton, who had to discover calculus in order to develop his mechanics. He did not know how to differentiate of the elementary calculus, but necessity arose, and what he ended up gave rise to the invention of calculus in mathematics. Heisenberg was in a similar state, that in his paper, this important thing that the variables occurring in Newton mechanics have to be regarded as matrices, and matrices are a form of operators, and operators don't commute. This was the highlight of Heisenberg's invention. This paper, when he wrote the first draft, was sent to Max Born, and Born identified the fact that what Heisenberg was doing was simply matrix multiplication. When he was writing X square, it is multiplying two matrices for X. Because Max Born, when he was in high school, his teacher had taught him what a matrix is. This is very interesting. To summarize what all I have told you so far, the theory must be based on observables omega and I of omega. Bohr correspondence principle is the guide. Action is quantized, and the Fourier decomposition of X in the omega space is very crucial. The Rees combination principle gives the clue to find the composition rule of amplitudes and frequencies in Heisenberg's approach. The examination of X square gives the composition rule of amplitudes. X needs two indices. In quantum mechanics, it is a matrix. Therefore, quantum mechanics is non-commutative. But I have not covered several things, and I list it as follows. Heisenberg goes on to tell us how to take over the dynamics given by Newton's force, that is x double dot is related to the minus the gradient of the potential. How to take it over to quantum domain? How to Fourier decompose x and obtain a perturbative series solution method? It was worked out by Heisenberg in this paper. He uses the quantization rule and shows how to calculate the values of energies which are observables. And he explicitly works out the anharmonic oscillator in one dimension. And he gives the prescription of how to manage non-commutative variables by symmetrizing appropriately. So the product of x and p, for example, can be written as half times x of x times p plus p times x. I give the references that I have used in my talk. The basic paper was by Heisenberg, the quantum theoretical reinterpretation of kinematic and mechanical relations, which appears in the source book of quantum mechanics, the book written by van der Waden. And two papers in American Journal of Physics, one by Fedak and Jeffrey with the title Quantum Jumps and Classical Harmonics, and the other by Hutchinson et al. With the title Understanding Heisenberg's Magical Paper of July 1925, a new look at the calculational details. I hope I have conveyed you the essence of Heisenberg's invention and the highlight of the fact that the Newtonian mechanics needs to be upgraded, and this lands you up in a non-commutative quantum theory. This is the end of my talk. I thank you all for your patience. If you have any questions, you can send me by WhatsApp. I would be glad to answer. Thank you all.
Thank you, Professor Sahoo. That was a very nice talk on a topic which is seldom discussed in usual textbooks. So it is a very crucial point that to be understood. So I think that it is a time for discussion. You can ask or comment your thoughts or questions. Professor Sahoo is here to hear you and comment you and answer you. So please. Yeah. Yes. Professor Murthy first, he raised the hand. Sir, your audio is mute, I think. Your audio is mute.
Murthy sir, your mic is off.
Somehow it is still mute.
So
Does it work? Does it work now?
Yeah, now mic is on, sir.
Oh,
Those who want to comment, either you can post in the chat box or you can directly talk to sir.
Okay. I think it's a bit complicated, and I probably gave a lot of mathematical steps, but they were crucial. And the observation that a very simple observation on taking the square of x and how to find the Fourier series for x square was all that was needed to arrive at the non-commutative fact that quantum mechanics is non-commutative.
Sir, audience have responded in the chat box, so you can look into the chat box. Sir. Many have expressed their appreciation here.
Where is the chat box?
On the right side, you can see its column chat.
Yeah,
on the right
Professor.
top.
Yeah, I think Professor BVR Tata.
Yes,
Sir,
but
please unmute your mic. Your sound is not audible.
Sir, your mic is switched off, I think. That is, sir, your mic is switched off.
Okay.
Yeah,
Yes.
yeah.
Okay.
Now we can hear
Thank
you.
you.
Yeah, please.
Sahuji, namaskar.
oh, namaskar.
Yeah, it's almost like 12 years. At least I'm talking to you over phone now. Very nice to meet you. And KPN Murthy is here, Leela madam, and Veena. Nice to see you, all of you first. Okay. It's wonderful that this is the second lecture. All of you are. Sundar Raman was there. Yeah, nice. Just two basic questions, Sahuji. One is you mentioned that automatically the light that is emitted will get a polarization after the transition. Is it, that is one my question, is it even if the incident light is unpolarized, do the transition makes it a polarized light? Which I think is, I'm not sure. That is one from your equation. Second question is, though magnetic field is also polarized, in case you put a polarized magnetic field, okay, not externally, the field associated with the light, will the polarization of the magnetic thing also can be seen after the transition? Any limits? Because we don't normally read these things when we do quantum mechanics.
No, the classical Larmor formula and the derivation, if you carry out it for one polarization, the same polarization is expected in the electromagnetic radiation. And so you mentioned the change of polarization. That is not possible in the Maxwell approach. And if there's a mixture of polarization, then each component one has to work out a classical theory using the same Larmor formula. It has to be appropriately superposed, taking the proportion of, let's say, vertical and horizontal polarizations. And that would be the prediction of Maxwell's theory. So there is nothing quantum about it. It is purely a simple fact of what a Maxwell equation would predict. And, what else you asked about the magnetic field? That is electromagnetic wave involves both electric and magnetic field. That is known as electromagnetic field. And the applied field is different. In the you have to have an.
So I'm talking about only the electromagnetic field of the light, not external field.
Yeah, what is the question?
So is we don't talk about after the transition, the magnetic states also get polarized. Only we talk about electric field.
Yes, because the magnet, the effect of magnet is 1 over c square. It is very, very low, very feeble. So in theory, it makes sense what you are talking. But in practice, it will not show up in any experiment. It is so small effect. I understand you.
So that's purely because of the strength of the relative strength of the electric and magnetic. Yeah. Thank you. Thank you.
Yeah, thank you, Tata, for your illuminating questions. Let me now go to Professor Murthy KPN. He has raised his hand. I think he is over phone. We'll come back to him later. Anybody else? From our students. Yeah. So I request our students to respond because this is a pretty good topic that one should catch especially the MSc students. Yeah. Today is not a working day, so you can speak out. It's a holiday.
Around 30 students are attending through YouTube
Yeah.
link. So because if there is any comment posted in the YouTube link, you can copy here.
Ramesh sir, do you have any comments? Ramesh sir, can you hear me?
Yeah, I can hear you.
Yeah. Do you have any comments?
No, actually, I want to say something other. I mean, after this discussion is over about Professor Valsakumar. So I'll postpone that thing for a later.
Okay.
Now, probably, since you asked, let me ask Professor Sahoo. How do you interpret this XMN? Is it a dipole moment or kind of thing? If you want to.
Well, it will be related. Simply multiplied by the charge, it will give you the matrix element for the dipole moment. You are right.
So just like Tata said, if electromagnetic field is polarized, automatically magnetic field also will be polarized because it is transverse. You don't have to say it specifically.
Yeah, by polarization, we only refer to the electric field.
Yes.
We never make any mention of
No,
magnetic
but
field.
magnetic field also will be polarized automatically because it is a transverse
Yeah.
field.
Okay, but that effect is so feeble, it is ignored in all calculations.
Yeah, but if it interacts with matter, but you need magnetic field, otherwise it will not propagate. Electromagnetic field, if you want propagation,
Yes.
you need the electric and magnetic field.
Yeah, they are together.
The interaction with matter, most effective electric field is the strongest. The magnetic field effects are little feeble. Yeah, that's what you meant.
Yes, but in Heisenberg's work, that was not the point, because he was not interested in how to deal with interactions. His idea was to develop a new theory, which is like, I will give an analogy. Simply by observing the falling of an apple, that was like observing the hydrogen atom. For Heisenberg, the Newton's falling of an apple triggered the discovery of the gravitation, a new interaction he discovered. It was similar kind of thing for Heisenberg, that by observing the spectrum of hydrogen and putting together all that was known about the hydrogen, but his interest was not to improve upon hydrogen spectrum or tinkering with bits and pieces. His aim was really high, to develop a theory which will be applicable to any microscopic system. And that was a very tall aim. In fact, when he talked about the fact that only observables have to be used, and to Pauli was his senior, almost same age. By the way, these are students of Sommerfeld, who is a great teacher, and Sommerfeld has produced half a dozen Nobel laureates. Among them are Heisenberg, Pauli, Hans Bethe, Peter Debye, Linus Pauling, but he never got a Nobel Prize, although he was nominated 84 times. And this fact that only observables have to be used is also interesting. This was the starting point of special theory relativity. But once Heisenberg gave a talk in Göttingen where Einstein was present. And after the talk, the two went for a walk. And Einstein asked Heisenberg, do you really believe that only observables have a place in theory? Then Heisenberg said, well, that was your philosophy, which I have used. And you did it it worked for you and you found special theory of relativity. Then Einstein interestingly said, well, at that time I thought like that, but now I don't think about, I don't agree with that. Theory can also have unobservable quantities, and that's very significant. But the simple thing that Heisenberg was guided was a philosophy which he just had a feeling that is it. You know, you don't have the electrons moving in a circle or an ellipse. It's very interesting. I may probably am going astray. I mean, outside the what? Is there any other commenter?
Okay, thank you.
I think Professor Murthy KPN have raised his hand. Sir, your mic is off.
Am I audible now?
Yeah,
Yes,
yes,
sir.
very well.
I just recently an anecdote in which when Heisenberg won the Nobel Prize, he did not. He was not in communication with Max Born for a very long time. After a year or two, he wrote to Max Born. He said that I was silent because I was feeling very guilty. The matrix mechanics was developed by you and me together, but I only got the Nobel Prize. I was feeling guilty. That was the reason I was not talking with you.
You are right. Max Born got it in 1954 or 52. Exactly, I don't remember. So many years after Heisenberg himself got the Nobel Prize in 1932. Max Born was his teacher, and Heisenberg was his assistant, a postdoc. And so he felt very guilty. He wrote a letter to him that it is.
He felt very guilty. And of course, Max Born won the Nobel Prize something like 20 years later.
Yes, yes.
Yeah, Professor Tata, you can speak up.
Your mic, please.
Your mic.
Your mic, please, switch on, sir. Yes, sir.
Sahu, I want because you taught a lot of things to this and also in quantum mechanics. If I want to teach, of course, because last year I taught to engineer, MTech engineering quantum mechanics. That's why I'm asking this question. I had a lot of difficulties. So because normally, as you said, we introduce quantum mechanics through Schrodinger equation and these things. And we work it out all the problems through Schrodinger equations. We don't normally introduce at BSc, even at MSc level, the Heisenberg formalism in detail and matrix formalism. But if I have to, suppose I completely ignore Heisenberg mechanism and go on, where do I get stuck? Or where do the student will suffer? This is one. Or you can inframe that it is better to start with Heisenberg formalism, though initially it is a slightly difficult thing. Then you will get much more insight. What is your impression with respect to this?
I have been teaching quantum mechanics for so many times. In the Sathya Institute also, I faced the same problem. Quantum mechanics, one is taught to you for this first time. It is just a bag of recipes that you do this. They have a wave function, you don't know what it is, and it is defined in a Hilbert space. It is not in the physical space. And Hilbert space of infinite dimension, to describe a free particle which moves in one dimension, you have to go to a Hilbert space of infinite dimension. Each value of x will be an eigen value, and it's very difficult to comprehend for a student. So I remember Feynman, it is attributed to Feynman, who said that shut up and calculate. Don't ask these deep questions about the meaning of what psi is. So that is the philosophy which all the textbook writers almost adopt. Giving you recipes of how to calculate transition probabilities, how to match with experiments, but that is not asking deep questions. and to really go deeper, because this will not take you very far. In getting something new, you just follow like a book recipe. You do this. This is called a matrix element. You take psi star and psi. And what is all this in classical mechanics? We never used any complex things. We are told that in the laboratory only real things can be measured. Now you are dealing with a complex valued function. It's a big jump conceptually from classical mechanics to quantum mechanics, dealing with a complex field. And it's very, very strange. Our students are never, they are brainwashed. They set up and do the calculation, generation after generations. So they are not looking at foundations. Only nowadays, the foundations have become interesting. And the whole field of quantum information has developed. But people who have used it, by the way, this idea of composition was what I was proposing to Valsakumar to write in the review article that I had mentioned in my
starting.
Valsa. The title of my would-be paper would have been The Golden Rule in Physics called Composition. That was the tentative title I had suggested to Valsa. And we had used that composition idea to examine various formalisms of quantum mechanics proposed in the literature. The same Weinberg gave a formalism of a Schrodinger equation. He added a nonlinear term and then said that the experiment has to test and whether quantum mechanics is really correct to that much accuracy. That appeared in 94. And we examined it, myself and Valsa, wrote a paper, and we examined his algebra that Weinberg used. And it is not composable. If you compose two Weinberg algebras that he has used in his proposal, they do not yield an algebra of the same type. So you go beyond the domain of quantum mechanics. And Weinberg, the famous Nobel laureate, my paper appeared in the letters in mathematical physics in France. And in fact, the refer title, which was not very much acceptable to the referee. He said, okay, you say a deficiency of Weinberg's quantum mechanics. That is how it appeared. But anyway, the review never appeared. Still, I have several manuscripts of Valsa still sitting in my cupboard, and they are not published. But those are, let me not go into that. Okay, thank you, Tata. I like that I spoke to you and also to Murthy.
Sahoo,
yes.
let me tell you my thanks for a really wonderful talk. There's been a very long time since I heard a good talk. Thank you very much. And I should also thank the organizer for arranging this meeting so very neatly. It is very befitting to the memory of the great Valsakumar. Thank you very much, the organizers.
Okay. Thanks for the questions.
Ajit, you want to say something?
Hello. Yeah. Good morning to one and all. A very wonderful and very befitting tribute to Professor Valsakumar sir. I just reminded of me when I asked some questions to him. He used to take hours together to answer from beginning to the end. Maybe this is kind of the generation people. If you ask the question, the answer will be always some 10 times of the content of the question itself. And it was a very wonderful talk, Professor Sahoo. And when we were teaching MSc students, this is a very new way of looking at Heisenberg quantum mechanics from Fourier series expansion and collecting the coefficient and introducing the non-commutativity in that fashion. It's a very new thing to me, and I have actually taken the photograph of the reference material which you have shown in the last, and I will be definitely looking at that. And thank you one and all for the organizers. It was a very nice organized program. program. Thank you.
Oh, I take it
So
as a
thank
compliment.
you. Yeah, thank you all for the comments and questions. I know that many questions are still remaining, especially with the students who are attending to our live streaming. And I advise them to catch up later through Hari Krishnans. Now, this time, let me go to invite Professor Sundar Raman. He is currently a visiting professor in IIT Madras, previously with IGSR, to share his experience and thoughts on Professor Valsakumar. Over to Professor Sundar Raman.
Can you hear me?
Yeah,
Yeah,
yes.
you're audible.
That's good. Okay. I had for the last 6 years of his Valsa's life, I had a close interaction with him. Okay. I will talk about that. Before that, during this talk, I got a good opportunity, great opportunity to see Valsakumar's classmates from MSc. Many people like KPN Murthy, Tata, Dr. Sahoo, who has worked with Valsakumar during different stages of his life, Valsakumar, as well as his daughter Veena Valsakumar. I could see all of you. Okay, what I will talk about is what I know about Valsakumar, about the personality of Valsakumar. Okay. His scientific contributions are well known. Okay, as Dr. Sahoo mentioned, maybe 30-40% of his work only has been published. Rest of them I know that is remaining as different drafts. Okay, I know Valsakumar from that time. He joined BRC training school in 1975. Okay, at that time, I'll tell about what I had seen about him and his impression. Everybody knows that he's very good in mathematics. So all the batchmates, I was 1 year senior to him. So all his batchmates, whenever any problem in mathematics is given, everybody used to go to him and say that you have to solve it. And he has some prize for it. Okay, that he has to give it, he will do it. So he was very good and generous in solving problems for all the students. And another aspect which I had seen is that he was extremely curious, and he used to ask probing questions to teachers. Because of that, what I had seen is, which I know personally when I talk to many people, many of them are afraid to go and take class, okay, during that time. They think that Valsakumar, that they are put in some uncomfortable position where they find that possibly that they do not know answer to many of the things which they are talking. Okay, that's it. And in fact, this quality he has, this is because science, I consider it is something is seeking truth. And there you don't compromise on it. You are only asking questions for which you do not know the answer. You are putting forward the question, you are looking for answer from others. And whatever work which he has done, he is very precise. And he knows what is the methodology which has to be adopted. He only uses that methodology. And not only in doing things, he is very precise in what he talks. Okay, he chooses the appropriate words. You can't find the better words. And he will not go unnecessarily talk about things. And when he has used some words and explained, you find that a complete explanation has been given. Okay. Personally, I came in great, after that, after finishing training school, he joined Kalpakam. So whenever I used to Kalpakam, I used to meet him occasionally. We used to have some chat, but we didn't have any professional interaction. Personally, I came to know him very well when he joined University of Hyderabad as a visiting professor in School of Engineering Science and Technology. So during that time, I used to ask him that you have acquired a lot of vast knowledge. What is the secret behind it? How did you do this? He used to tell that the secret essentially is that he used to spend a lot of time in library. Right from his BSc days onwards, he used to befriend all the librarians and have a duplicate key of the library, so that anytime he wants, he used to go to library and use that facility. So almost his waking period, he has spent time in the library and acquired a lot of knowledge to read and understand. Almost he is like a self-taught man, that is read more from the books, reading it himself. Okay. Then in BRC training school, not training school, at University of Hyderabad, I had seen him that almost every day he used to take about something like 2 hours of lecture will always be there, almost like it's about 10 hours of lecture in the morning. In addition to it, every day in the afternoon, a few students will come that we have some doubts, we wanted some clarification. So in the afternoon, with some about maybe 5 to 10 students in his office, he used to give lectures for maybe 3 to 4 hours almost every day. That was his passion for passing on knowledge to other students. Okay. Another aspect of him which I noticed is that essentially the human side of it. That is, he knew that many of the students who wanted to acquire knowledge, they are very much interested in it, learning the subject, but he knows that financially they have a problem. So he used to buy books and used to give books to them so that they can read. For many students who have a problem, he has purchased laptop and given to them so that they can use it for doing the work. He has gone out of the way to help students so that they come up in life. And when students want some places where they, after finishing the work, even he has helped them a lot. I always consider him first as a mathematician, then as a physicist. Okay, he has a very deep understanding of the subject. Okay, especially in the last few years of his life, at least for the last 6 years when I had interacted with him, what he used to tell was that he wanted to work on many of the unsolved problems in quantum mechanics. That was his ambition. In fact, he has been buying a lot of books, and I knew that whenever I used to visit him in Thrissur, he used to read that. And in fact, he wanted to write some 2 books before he is dead. But anyway, that did not happen. But he started writing some initial, some part of it. One is on probability and statistics. And the second book which he wanted to write was on many world theory of quantum mechanics. These are all the 2 subjects which he wanted to write a book. He made some initial beginning, but anyway, afterwards his health deteriorated, so he could not continue further. Apart from his deep interest as well as knowledge in physics, he is a very versatile, all-round person. Okay, not only in science, he has a very good knowledge in various aspects of philosophy, literature. He is a very voracious reader. In fact, when I used to visit him, I used to see books in the library, and he has read all of them on all the 18 Puranas, all the Upanishads. Some of the books, I think, which are banned books, which are there on different philosophies, which he has read it. So he is a person who is, I should call it as a karma yogi. He does things which is, and he is very selfless. He does it everything for others. Okay. In fact, I had a good fortune to have a close personal association with this great soul, Valsa, for his last 6 years of his life. I treasure those moments. I thank Association of Physics Teachers Kerala for giving me an opportunity to talk about Valsakumar. Thank you very much.
Thank you, sir. Titus, sir.
Okay. So thank you, Professor Sundararaman, for your splendid words.
regarding your memories with the Professor Valsakumar. The words are actually highly inspiring to the young teachers, especially to know that one has to read extensively. That is the easiest way and also the hardest way to achieve your dreams in future. And it is sure that from the words of Professor Sundararaman, how this character is building up a man. And we have seen that both in teaching and also in human side, he was a great man. It is very nice to hear that, especially to our APT young teachers. Now, let me go to Professor Ramesh Babu from Department of Physics Research. Earlier, he said that he want to say something about Professor Valsakumar. Professor Ramesh Babu, sir.
Hi, thank you. Can you hear me?
Yes.
Yeah. I would like to say something slightly different from these people are saying. Last year also, I attended the meeting, this memorial thing. In that meeting, there were no people who was associated with him before he went to Kalpaka. This time, there are two people. I can see Dr. Krishna Kumar and Dr. Ramesh. So I would like to one of them or both to give some of their thought about him, because it is a MSc students period, you know what a person is. So I request them to do that thing. Before I stop, Ramesh is my super senior. His senior is Valsakumar. When we are doing MSc, we know about Valsakumar. In fact, I should say he was a legendary figure, because we heard from our seniors about his, somebody has mentioned about library and other thing. Probably Ramesh and other people can explain what was the culture in that Calicut University at that period of time. So, unfortunately, I was not personally associated with Dr. Valsakumar. There are only few occasions I was associated. I met him. One is when I attended Ramesh's son's marriage. He and his wife was there. Secondly, when Valsakumar came to physics department to give some lectures, we met for a very short period. What I have to say is, see, I am also a teacher. If you attend this class, there are a lot of things a teacher has to learn from him. Of course, I am retired now. I don't know whether I can apply it now. But I attended this class in a very late stage. So personally, I was not very closely associated with him. But I'm personally very closely associated with Ramesh and his classmate Krishna Kumar. So I request Titus to call upon them to give some thought about him during his students' days. Because students' days are the thing, In my hostel days and student days are the thing you have to share. Because I think I request Titus to do that. Thank you.
Yeah, thank you, Professor Ramesh Babu, sir. It is a nice comment that we can go to his real colleagues or classmates. But I think before that, especially we are in memory of a great teacher. So along with hearing from his friends and colleagues, I think it is better to hear some words from his family members. Leela Valsakumar is there and Veena is there. Maybe Veena can speak.
Okay, can you hear me?
Yeah, yes.
Yeah,
Yes.
so firstly, I'm happy to see all of you. lot of familiar faces. I can just see about 9 faces on the screen right now, but very happy to see Sahoo uncle, Sundaraman uncle, Murthy uncle, Ruchi uncle, Ramesh uncle, so many people, so many familiar faces. Yeah, I couldn't really participate in the first memorial lecture because, that was organized at Alwa, but I'm happy to participate in this one. And in particular, I'd like to thank Sahoo uncle. So, I've been writing to him, and he has been, he's taken extraordinary efforts to record the presentation, the talks, and I know there has been a lot of back and forth between APT and Sahoo uncle, so I'd like to thank him for all the effort he has put in, and the lot of fine-tuning efforts which has gone into this. And I also thank APT and everybody else who's joined this lecture today. Thank you all.
Thank you, Veena. Now, as Professor Ramesh Babu said, we can say briefly to here to Professor Ramesh.
Ramesh sir, your mic is off. Please switch it on, sir. Ramesh sir, the mic is off.
No, maybe he is attending.
Your microphone mic is off.
Mobile mobile screen learn touch ചെയ്താലും മതിയെന്ന് തോന്നുന്നു.
Yes, sir.
Yes.
Yeah, first of all, let me congratulate the organizers, and I'm hearing all the time. Yeah, I want to share a lot, I have to speak, but speaking about the university days, he was my senior, just senior. One thing to remember all the time is wherever there is injustice seen, he will react to that. That is the nature. So you want to react to, actually that shows that he want to always be in a real space, wherever there is some injustice, right? That approach is there even in his university days. He will, any problems, if teachers are all also sometimes scared, because whatever be the assignment given to him, he will be submitting. He is the first person who submits all the time. He will go to somebody was mentioning about the library process. Yeah, that's true. In the university days also, all the time he will be spending time in library, and everyone knows that his talent in mathematics. And juniors, whenever there is a doubt, everybody will be approaching Valsakumar. I do remember that days when there were seminars for us, and even tough problems. He used to select tough problems only. I still remember his talk on Green's functions first semester, when we are finding it very difficult even to understand about integral differentiations, integral equations. He was very confident. So his intelligentsia in mathematics is really appreciable, and that is what he made him. He himself used to say, whatever he knows is nothing other than mathematics. Whenever in personal talk, whenever we had, he said only he knows that he knows some mathematics. Just that through that he only come to the physics, nothing more than that. So he can approach any problem, whether it is in biology, whether in social science, he will be looking through mathematical angle. That is his quality. And another quality is, as Ajit said, if you ask a problem to him, he will sit 24 hours to that. Even if he forget, he will remember that. I too had so many experience when interacting with him. We had some few papers with him. When I have some problems, we will be leaving that problem, but he will remember that. So many such issues are experience are there, but I forgot some of them. So he's the person who is dedicated to science. Quality as a person without much ambition in any other thing. Just to do science, nothing other than that is. Invention is science, nothing more than that. Science means physics. So he's a wonderful person, and his loss is a great loss because he should have lived so many years, for so many years, naturally. Would have been help to many students and physics as well as mathematics community. It would have been a blessing. And even when he was in IGR, he used to interact with the university. He was in our board of studies. And I was at the department. He visited for several times. Of course, I thankful to Dr. KPN Murthy also. They used to come together for some workshops, just mainly because of their interest in teaching. Is one I appreciate. We all appreciated his quality as a teacher. KPN was also with him. We were together here. They were interested in teaching. Even if you are scientific inventions, whatever you find it out, they are of the type of persons who realizes that should be given to the students. How something has they found out, what triggered that such an invention or whatever is that. That's the type of thinking they have, and that should be communicated to the students' community. Then also they will think about like that. So definitely, Dr. Sahu's lecture was really wonderful and inspiring. How to such a problem? What is the turning point of such a thinking? That is what has to be motivated. Because now we are thinking in a different realm. What's the real situation that triggered such a thinking? That is what should be insisted to the students. Then only they also will think like that. And in that context, Dr. Sahu's talk is really wonderful and inspiring. Actually, thank Professor Rahu. And that is the type of persons. Professor Valsakumar is also like that. He will take him to the real situation and motivate. What made him to think like that? That is what his quality is. And a person, as I told you, is a wonderful person. And I have a lot to speak. But thanks for the organizers for giving me an opportunity. Thank you.
Thank you, Professor Rameshan. That's the words from almost a classmate of Professor Valsakumar. Now, Hari, we have to go to somebody else.
Yeah, Krishna Kumar sir is here. Krishna Kumar sir is here.
Yeah, Krishna.
His classmate.
Yeah, sir, please, Krishna Kumar.
Good morning, everyone. Can you hear me?
Yes.
Yes, yes.
I didn't expect it to be making any statement here. I was mate of Valsan and Leela. In fact, the very second batch of the MSc program at the Calicut University is the department. I remember Valsan very vividly. I mean, there is no one could, and of all these years. See, Valsan was essentially one of the most brilliant mind I have come across. And it is naturally in a tradition, the way I came up with a very extremely competitive spirit. And it was Valsan who really put me in my place. So it was basically such a sort of an inferiority complex in me because the sheer brilliance of the person. One of my friends used to say that he has absolute photographic memory. Anything, and he remembers, understands everything so thoroughly. Of course, those days we had to, of course, we being the second batch, we had to go through. We are fortunate also to go through a real serious courseworks, and which benefited all of us very tremendously. And I always felt that Valsan is one person ended up in the wrong place. I thought in the BA should have been in a far more academic settings, and where he would have done far more. This is one of my feelings, which may not be true. I'm just talking about myself. And another characteristic which I noticed about is this self-effacing nature and selfless nature, and don't go for any of these accolades. But I would like to make a statement is that Wilson did not deserve the sort of accolade which he did. We did not get the sort of accolade which basically I believe that it has to do with his nature, which on the whole, if you look at the science in the country as a whole, is not a good thing. Feel that it is not good of him, history. And as a result, the science as a whole in the country suffers. This is my opinion about the Indian scientific scene. After departing in 75 from the university, I met Wilson in 1992 when I visited Kalpakam for to provide some technical help to one of the groups there. I still remember having dinner with him, Leela and Veena. Veena was a small girl at that time in their house. Later on, I met university, some of the celebrations in the university. I remember him talking about quantum mechanics in one of the talks in the afternoon, which was organized, and he gave a 2-hour discourse on quantum mechanics, though I don't remember the details. So later on, I came to know when Wilson was not well. For some reason, I had called him. And then he told me that he was not well, getting back to work. But unfortunately, that was not to happen. It has been an extremely great loss for us. I mean, it's not, I would say for us, it is a great loss for the Indian science as a whole. I don't have anything more to say. I wish this program, which have been initiated at IIT Palakkad, all the best, and have an excellent career in it. Thank you.
Thank you, Professor Krishna Kumar. If there is anyone else would like to speak,
we can move on to vote of thanks.
okay. If so, let me invite Dr. Rashmi for the final words. Vote of thanks. Rashmi, okay.
Hello, audible or no? Hello, am I audible?
Yes.
Good morning to one and all. On behalf of Academy of Teachers, it is my privilege to propose a vote of thanks to this grand academic event in memory of our loving teacher, Valsa sir. As most of his colleagues and friends testified here, definitely he was a passionate teacher, and above and all, he was a very good human being. Commemorating Valsa sir on the second memorial lecture, on behalf of Academy of Physics teachers, I would like to extend my heartfelt thanks to Dr. Debendranath Sahoo, Honorary Professor, Sri Sathya Institute, for delivering a very informative lecture on Heisenberg's invention of quantum mechanics, which is a very less discussed topic in standard textbooks. Definitely, this had been useful to both students and the teaching community. And this lecture was actually a recorded one. And as per the suggestion of APT, he had agreed to record this video. And in spite of his personal difficulties, he had recorded it multiple times and to make this a perfect one. And there is no words to thank you, sir, for the commitment and the effort you have taken to make this event a grand success. Thank you very much, sir. There were almost 100 participants who were attending the lecture, both from YouTube as well as the Google Meet. So once again, on behalf of APT, thank you very much, sir. And with utmost love and respect, And on behalf of APT, I would like to extend my heartfelt gratitude and thanks to Leela teacher and to Veena for their presence and also for their support in activities to student-oriented activities of APT. Definitely, without any doubt, we are sure that it will be useful to generations of students. Thank you very much, teacher and Veena, for your presence and support. On behalf of APT, next I would like to extend my heartfelt thanks to Dr. Sundararaman sir, the visiting professor of IIT Madras, and for sharing his memories of this beautiful friendship with Valsa sir. And thank you very much, sir. And I would like to extend a heartfelt thanks to all his former colleagues and friends, Murthy sir, Sridhar sir, Krishna Kumar sir, Rameshan sir, who have shared their memories of Valsa sir. Thank you very much, all of you, for your presence and also for the support on behalf of APT. Next, I would like to extend my heartfelt thanks to students of Valsa sir and teachers and students who are all present here. And once again, thank you all for being here and for making this event a grand success. Thank you very much.
Okay. So, Hari Krishnan.
Yes, sir. You can declare the meeting also.
Yeah. So it was a fine meeting, and we are all, especially the APT members, are really indebted to our great teacher, Professor Valsakumar. It is true that a great teacher will always be remembered through his colleagues and especially in his students. We, APT, even though we are not become the part of the students in his real teaching days in the institutions, but after that we got a lot of opportunities to hear directly from this great teacher. We are really indebted to him, and sure, all our APT teachers and students will always remember this great man. It's really a loss, especially a man who is well versed in basic mathematics and especially in quantum mechanics. It is a real loss to us, but anyway, we will the knowledge or the lectures he shared with us will be always be with the teachers of APT, and we will always remember. Thank you.
Thank you all.